Okay, so let's continue. Um, so in this video, we're going to talk about model validation. So this is one of very important concepts in practical machine learning. So basically, we need to find a metric to evaluate how good of our model could be. So this video is about concepts. In the next video, we're going to talk about some very practical and examples of so those evaluation metric with all these like programming concept and programming and examples. Uh, Usually, there's no unique way to do this kind of model metric. We select the models by a lot of so multiple metric. So and for example, if we work with the supervised learnings, so we usually talk about the loss functions. So basically, that loss functions measures how good this model is predicting the outcome. So basically, how close our like predictions close to and the ground truth. So we're going to design this kind of like loss functions to make sure if we have a less loss, then we have a better in terms of matching into our outcomes. There are other like metric to evaluate the model and the performance, for examples. And for the classifications, one of the very important one, and which is accuracy, we're going to talk about momentarily. Another one is like, for example, MAP. I mean, so this is being used a lot in object detections, but there are other and a metric other than those of this. For example, they, I mean, could be like business specific. If we are talking about, we are trying to build models for so very much business and a related problem, we can talk about the revenue. And the revenue could be one of the metric because that's the thing that we want to and make sure we can and have a better and revenue if we make any kind of business and decision. And also, for example, the inferences latency. I mean, this is also very important because and we don't want our customer to wait for too much time. So this is something that we can also take into our considerations. And we are going to talk about both of that as well. But in the homework, if we I mean the homework, we usually give you what kind of metric we are going to and work out. There are and a lot of reasons why we want to choose one specific metric. But that's something. But in the real practical problems, it is your own decision to choose the right metric to work with. Okay. For example, the simplest way we can and work with is binary classifications. Binary classification problem is like the basic problem. Think about it, you're trying to distinguish cats and dogs, or like there's all some like similar problems. I mean, this is some like very fundamental problems in the practical machine learning. So the first thing is the metric is accuracy. So this is one of the I would say the the most important thing. So basically, it's our correct predictions divided by the number of examples. So that means we're trying to find out if my y, so the ground truth is actually equal to the prediction. So that indicates it's a correct predictions, and it divided by the number of the examples, which is the y. The second thing is like precisions. So we have a true positive, and it divided by the prediction to be positive. Since we are talking about binary classification, so that means it's either 0 or 1. So the numerator is that means so the prediction is equal to 1, and it is actually equal to 1. So this is the true positive, and the like denominator is basically the prediction is precisely equal to 1, which is positive. So this is called precision. And we can see this is different from accuracy here, because in terms of accuracy, we also consider the accurate predictions for y and y hat equal to 0. And the denominator is the total number of the examples. That's different from the precisions. So this is a commonly asked questions during interviews. What is differences between accuracy and precision here? Also, the next important concept is called recall. The recall is true positive divided by positive examples. So the and as a numerator is the same, but the denominator is actually y equal to 1. So that means is it's a truly so positive and examples. In the position, the denominator is our prediction is equal to 1. So that means y hat is equal to 1. But in the recall is y equal to 1. So that's the differences on the denominator. So you have to be careful. Sometimes if and the denominator will give you 0 for either y hat equal to 1 or y equal to 1. So if we have a very few number of the positive and in cases you might have encountered that the denominator equal to 0. So there are like one more metric actually balance both of this. So it's called F1 score. So the F1 score is the harmonic mean of the position and the recall, which is 2 times P times R divided by P plus R. So this is, you can think about as a harmonic mean of these two and the two like metric. Both metric is very important. In the next lecture, we're going to talk about under what kind of situation you should use at a precision, and under what kind of and a situation you should choose the recall. So like there's no universal way to choose position versus and a recall. It actually depends on the scenarios or what kind of problem you want to work with. Okay, so the other one is being very popular is called an AUC ROC. So AUC ROC is actually measure how well this model can separate these two and the classes. So basically, so we're trying to choose a threshold. If the prediction is actually bigger than this, this threshold theta, you're going to predict this is positive. If it is less equal than theta, it will predict as a negative. So this, you can see right here, this is my an ROC curve. So basically, this is true and the true positive predictions and the positive examples. It's called TPR. So this is precisely equal to the recall. So this and the vertical axis is my recall, but x-axis is my is the FPR. FPR is false positive predictions divided by the negative examples. So this is kind of the opposite of the TPR. So if we plot this is versus and using the x and the y axis, it gives me a curve. So that means if we and change this like threshold, and it would, if we like varying this threshold, it will give you a very different and the TPR and the FPR. So once we varying this theta and that curve that give out is called an ROC curve. And we're going to talk about how to get this ROC curve using like the code in the next videos. And what is the AUC? And AUC is area under the curve. So basically, it's the area under this shape of this ROC curve. So this is basically says this ROC curve is always and above this diagonal line. So that indicate, and usually it will be above this diagonal lines. And then, so that means my AUC value should be and between 0.5 and 1, because we know the diagonal actually is give you the ones. And also like this value, since this is percentage, so all the x and the y axis should be has the range from 0 to 1. So it's all like in the and 0 to 1. Okay, right here, that give you one simple examples right here. So say if we have a perfect separations here for the problem, so that means Okay. Wait a minute. Oh yeah. So I mean, if we have a perfect and a separation right here, whoa, true positive. Oh yeah. So if we have a and this like and the perfect separation, so that means we only have a true negative and a true positive. So that is true negative. That means if it is like negative and I predict to be negative, true positive, that means if it is positive and then I predict to be positive. So that means these two and actually has a perfect separations. All I need to do is put this threshold at 0.5. Then these two and the classes has the perfect separations. If we have a perfect separations, then AUC is equal to 1. That means all we need to do is just have a like basically a straight line at once. So that and the area underneath of that will be precisely equal to 1. However, on these two cases, for example, in this cases, I have a majority part to be true positive, but there are small portion to be false negative, and there's small portion to be false positive, and that's the large portion to be true positive. So that means, I mean, this is the cases that usually we will see in the practice. So you will see something like the curve like this. So this is, so the AUC right here is 0.7. So that means the area under the curve, which is 0.7. So that indicate the, I mean, the model performance is not really good, but it's, I mean, it's doing some okay job. However, on the next level, which is not separable, so basically the classes is completely overlap to each other. So so as a result, this ROC curve is I mean on the diagonal that indicate both classes on this binary classification is not actually possible to separate. So this AUC here is actually 0.5. The last cases is it's kind of the flip the signs here. So this is being like it's like the curve will be like this. So that basic says everything here should be 1, but it's predicted as 0. Everything here is 0, but predicted as 1. So it's kind of like 0 and 1 being flipped. But that is okay because this is still perfectly separable. That means if my AUC right here is just precisely equal to 0, that indicates we just mess up with the 0 and the 1s. All we need to do is just switch in the 0 and 1. Then we have a perfect separations. So this gives you some idea what kind of things that we're working with. We just measure how good the model are separate these two classes. So this is so the metric of AUC ROC, which is a very popular and well like and studied metric. Okay, so I mean the next I'm going to just talk about one very simple and case studies. So this case study is being used a lot in practical. So basically we are trying to display like ads once I mean like say in google.com. So once you do some search, there will be always some ads on the top of the uh and over there. So basically this is basically the pipeline that we're going to work with. So we're going to say and we have like some query, for example, we search certain like word on like certain pages. So that means I'm going to retrieve some related ads. So that means, and that ads will coming from some recommender systems. We're going to talk about or work with recommender systems later of this courses. And the next we're going to, and we're interested in the estimated click-through rate, CTR. So this is basically a classification problem, which is binary classification problem. That means if I show this ads to the consumer, how and whether this consumer will click this link or not. So and what is the probability actually click this link or not. So this is a very interesting things. So and also so that means we're going to and display the top ads ranked by the CTR by prices. If the customer click this link, then the like website or the google.com will receive certain amount of price. So this is something that we are interested in, and we are interested to maximize because we want to make sure CTRs multiply the prices to be maximized as much as possible. So this is, and then this is what I'm trying, and just we talk about this. This ads is basically the major revenue sources for almost all internet company, for example, the Google's. But this is something that we are thinking, and then that CTR multiplied by the price is also a very important metric. But that's not the only metric, because we need to also optimize both the revenue and the customer experience. For example, the latencies. It should be, and the ads should be shown to the user at the same time as others. You don't want to wait for 1 second, 2 seconds for this ads to show up, because for 1 second to show and 2 seconds, the consumer will not look at this like ads because it will take too much time. And also the ASN, which is average ads shown in one page. So you don't want all the ads to be shown in one page that it's all ads. That's really bad, and the customer experience will be really, really bad. So you don't want to have something like that. But you also don't want that there's no ads shown in the page. Basically, you won't get any money for that. So as a result, this ASN should be reasonable values, for example, 3 or 4, so that the customers will have reasonable chance to click that, and while still maintain very good customer experiences. CTR, we have a talk about that. So this is basically being in a study with the models. CTR is actual user click-through the rate. So this is the user and ads. So, and this can be predicted through this binary classification problems. And last, which is ACP, which is the price, which is average price advertiser pays per click, which is given from the advertisers. So these things we also need to consider, because not each website will pay the same money to the internet companies. Some companies will pay more, some companies will pay less. So the way actually we should think about is there will be the balance for those high paid companies and versus low paid companies. So this is basically the average price for those advertisers pays per click. So overall, this revenue should be multiplications for those factors altogether: number of page views, ASN, CTR, and ACP. So at the end, we're trying to maximize these revenues while maintaining as low latency as possible. So this is very important. We are not trying to maximize one single metric. For example, for the binary classification things, we can do and make models for CTR very well, but that's not the things that we're trying to do if we want to work on the business problem, because in business problem, the most important thing is we want to maximize our revenue, and that's how we calculate the revenues, right? So this is how we actually do it. And also, during displaying, the ads, so this will be model metric to the business metric. So basically, the key and the model metric that we're going to do is AUC. But we need to think about a new model with increased AUC may harm the business metric as well, because higher AUC, maybe lower estimate CTR, then they will have less ads displays. So because in order to have a higher AUC, then we have a higher confidence with our metric. Then as a result, then we have lower CTR, and as a result, we only have a lower ads displayed. And for the lower ads displayed, we only have a good and to ensure we can have a good ensure those ads will be clicked. But that's not good because I mean less ads displayed, less money we will be made. And also and the lower real CTR because we train and evaluate in the past data. Once we have a new data and things will could be like and dramatically different. And also and increase AUC, as I said, may lower the prices or and we might focus on those like lower prices and the lower like ACPs. But with the lower ACP, although we can get like higher CTR, but still we might lose like big amount of revenue as well. So I mean, we should consider everything into together and consider as a balance with all different factors into our account. We cannot just consider this AUC to be one single metrics that we'll be working with. And also, I mean, if we want to work on like those kind of practical problem, at the end, we need to deploy this model to evaluate these real traffic data. So to see whether we can make money or not. And a lot of cases we build the models, find out the best parameters, but we still need to test with the realistic data set to make sure it actually can make the the monies that we want. And also so this is a quick summaries of what we have been talking about. And so we basically evaluate models with a bunch of and a multiple metric. And these metric evaluate performance on examples, for example, accuracy, position, recalls, F1, AUCs for those binary classification problems. So these are being very popular used in those classification and binary classification problems. If we are working with, for example, other problem, for example, and unsupervised problems like clustering problems, those metrics could be different. So here we're just talking about classifications. This business metric actually measures how model impact the product. So so there's a product metric, there's a business metric. At the end, we want the business to be successful. So at the end, the business metric is the thing that we should consider. But so business metric is much more complicated, and so as a result, this model and metric will be just like only a tiny part in to be considered in this business metric. And a business metric is much more complicated things that we need to consider. All right. So this is basically a very quick concept and introduction to and a conceptual introduction to those model metric. On the next, we're going to talk about a very, very important concepts, which is called an overfitting and underfittings. This basically shows up almost everywhere during machine learning problems. So, and for example, and the lender hires you to investigate who will repay their loans, and you'll find out, and you have information or the data for 100 applicants, and you find out 5 actually default within 3 years, and you'll find out that these 5 people who defaulted all wear the blue shirts during interviews. Your model may just take this as a strong signal. That means everyone who wear the blue shirt during interviews will default. You know how ridiculous of this is being, but this actually happens a lot of times during this machine learning training here, just because we need to think about that there are 2 very important types of errors in this and the machine learning. One is training error. Training error is actually the model error on this training data set. So that's things when we train this and the models, we want to minimize the training error. There's another one is called generalization error. So this is the model error on the new data. So this is something that you work with, and you work and a lot and times to think about if we have a testing data set as treated as a new data set. You never seen that during the training process. You want to make sure this model error to be small as possible. So the bottom line is we want to minimize this generalization error instead of training error. Training error is important, but at the end, we want to make sure our generalization error to be small as well. So this gives you a very quick overview of things. So this is basically generalization error and the training error. It will be good if we have like low training error and low generalization error. So that means we have found the right models, and it's almost correct to say our model is doing a very good job. If you see your training error is high but generalization error is low, that means and you probably have some bug. It usually happens a lot of times that somehow this during the testing or validations or whatever the new data you're feeding, it actually it's leaked from the training data. So that basic says those new data may not be the new data at all. So that happens, like there will be leakage of the informations or the data and the data during testings validations. So this will be bad. So this usually happens if you have a bug of your code. On the next, if your training error is low, generalization error is high, this is pretty much very common. And one of the things is like overfitting. So that means you can have a very low training error, but turns out if you have a new data, it cannot predict very well. So this is very dangerous. This is called overfitting. Another one is your training error is high and your generalization is high. So basically, your model is not learning much. So this is the region of like underfitting. So these two things is kind of balance between like underfitting and overfittings. So this happens a lot in a lot of cases. And also, it can also give you and a lot of information from the model complexities. For example, we can think about the like linear regression is like less complex. However, like neural networks or like random forest, it's much more complicated. So if our model complexity is low, uh, and our data complexity is also low, so basically a straight line of the data, and you're using the linear regression to make predictions, so that will be really good. I'm actually doing a very good job. So if it is a straight line, however, we are trying to using very high complex model, for example, like and regression and using like a very high order of polynomials, trying to fit those points. So that means we are trying to make sure those points are being passing through all these and training data perfectly. But sometimes it won't be a very good idea, because if you passing all those points on the training and data, it gives you a lot of zigzags. It doesn't generalize very well. And as a result, it actually gives you a lot of overfitting for those data that you don't see. That would be really bad. At the same time, if your data is actually very complicated, which has a very high complexity, but you are using like simple model, for example, linear regressions. So that will be the situation you will encounter for the underfittings. So these are the two situations you will have like encounter all the time for the overfitting versus underfitting. So you should be consider your problem. You need to visualize this data and to understand what kind of model you should be choose, as whether you want to choose like low complexity models or very high complexity models. It is not always good to choose very high complexity models. It might easily get overfitted. So that's why this is very important. So, and what is, the model complexity here? So basically the model complexity is the capacity of these models to fit the data points. And for example, in this cases, machine learning, model complexity is basically the number of the learnable parameters. And I think about, the linear regressions, the learnable parameter is pretty limited. This is only like NAD plus one parameters need to be learned. But if we, for the neural networks, it could be like a lot of more, like D squares, or even like hundreds or like thousands more parameters need to be learned. And also you need to consider the value range of these parameters. if the value range is very big, like from minus infinity to infinities, then this model complexity is high. And versus the model and the value range of these parameters is only range from very small or very limited range. Then in a lot of cases, this model complexity will be low. And but in a lot of cases, it will be very hard to compare between different types of like machine learning models to see which one is more complicated or not. But think about and regressions. If you are talking about a linear regression of a degree of 1, usually this and the model complexity is low compared to the linear or the polynomial regressions with a degree of say 9. That would be higher model complexities. So these two actually can compare. But if you are talking about a model of decision trees versus neural networks, you probably cannot compare that easily because they are different type of models. With a different type of models, it's not easy to compare. There is a way that you can actually compare. It's called a VC dimension. So you can think about it's a maximum number of examples the model can shatter. So basically that dimension tells you and the capacity of and then the models can do. But usually in a lot of cases, this VC dimension is nearly impossible to calculate or even to estimate in general. So it will be like quite messy. Just give you some theoretical guidance for the kind of problems. For given specific problems, the VC dimension basically cannot, and you cannot find that kind of VC dimensions. All right, so right here, so this give you a good idea. So this like vertical is my error, which has two type of error. One is generalization error, one is training error. So, and then this is my model complexity. If my model complexity is low, then your training error and the generalization error are both high. And the most important thing is the gap between the generalization error and training error is small. That is the range of underfitting, right? So, and the underfitting is both error is pretty high. And also the gap between both error is small, right? So these are two things to indicate we are in the regions of underfittings. However, as model complexity getting more and more, for example, we are working with much higher order degrees of the regression, then the training error start to decrease is dramatically to be very, very small. But as a result, the generalization error start to increases. So so then there will be a gap between this generalization error and the training error. So this gap tells you as model getting more and more complex, it turns out this generalization error is getting bigger and bigger. There will be start to showing a big gap between both errors. So that range is actually the overfittings. So this give you, so this plot give you some idea when this will be underfitting, when it will be overfitting. So this give you a very good pictures, and for both situation. And of course, what is the optimal model? And the optimal model is reached for this generalization error to be the minimum of that, right? So that would be the cases that so the right models you should be choosing from. In general, that would be very hard to find because generalization error is very hard to approximate. And then later I'm going to show you this generalization error can be roughly approximated, but in general, there's no way to find like calculate this generalization error analytically. So we can approximate this optimal model right here, but this is like a bunch of methods that we can do. One of that is just called like and model validations. So let me just give you one simple examples for this model complexity in and then with the decision tree. We're going to talk about decision tree later on. I mean, as of this course, I believe you guys already have some certain exposure for this decision tree right here. So basically, this decision tree actually has a one important parameter. It's called maximum depth. So basically, how and how large of this trees look like. This tree size can, I mean, it's actually controlled by the number of levels, and which is the maximum depth right here. It turns out that the higher the level it is, the more complex of the and the model it is. So the lower of this level it is, I mean, the model will be less complicated. So this is something that you'll be see. I mean, it actually. So if you trying to plot training error and validation error, so we are using something called validation error to approximate this generalization error. So if we plot and trying to plot this out for and that our like house sale data that we have, we actually can see this trend exactly right here. I mean this trend here. So you will see our training error decrease monotonically. However, our validation error will decrease, then gradually increases. So you can see it actually shows a large gap right here for the maximum depth, about 40, 50. So this indicate with this region, this actually is overfitting. On the other hand, right here, so both error are very high, and the gap between both areas is small. So that indicate this is the region of unwanted fittings. So the optimal parameter is about 10, 12 right here. So this will be the best optimal like number of levels that you should choose from. And also right here, so we have talked about data complexities. Data complexity is quite complicated. There are multiple factors matters. For example, the number of examples, number of features in each examples, and how hard to separate these classes. Again, it's very hard to compare among the very different characters. For example, if we are trying to compare with the natural language processing with a character versus image using the pixels, it's very hard to compare. But I mean, to be more precise, there is something called Comus graph complexity. You can think about as it use something called so whether it's a simple model or complex model. So you can think about if the data is simple, if we can just using a linear regression to and to like and separate that. If the data is more complicated, we actually have to using like a deep neural network to separate that. So this is give you some idea right here. So this is my data complexity here. When my data complexity is small, that means we should choose the simple model instead of more complex model. Because if we choose more complex model right here, it will have the overfit. Then the complex model, that generalization error for the complex model is even higher than the simple models right here. But like more complex model will need more data if we need it. Then and we have more and more data, then that data complexities is actually increases. So if we have a more complicated data, then we should choose the complex models. I mean, instead of simple models, because if we think and choose simple models, this generalization errors will remain pretty high. But if we choose complex models, then that generalization error will like significantly decrease right here. So so this whole thing actually depends on what kind of data you are working with. But of course, I mean, in general, you cannot decide how complex your data you are working with. So this is some mathematical like formulations that we can work with. But I want to emphasize. Oh, so this is basically something called something using this like and the statistical learning theories to see those kind of like and the generalization errors for and the differences between so sorry this and the gap between the generalization error and the training error right here. So this is the gap right here. If the gap, I mean, so if in the overfitting regions, so this will be pretty high right here. But of course, I mean, so that all, I mean, depends on that VC dimension, which is in general we don't know how to and approximate. And also, this generalization error also depends on the training algorithm that we are working with, because we can add regularization terms actually can like penalize these complex models, and to make this like complex model to be more simple and to be simpler. And also, we can use this like stochastic gradient and descent method to generalize and to train the model. And usually with like stochastic gradient methods, it actually can generalize better compared to using gradient descent methods, because it's less susceptible with and those outliers. So overall, this is basically like concepts that you should be think about for those model selections. You should pick a model with a proper and a complexity for your data. You should like and visualize the data and to understand like how complex of this data that you have. The main goal is you want to minimize the generalization error. It doesn't matter whether you minimize the training error or not, but the ultimate goal is we need to minimize this generalization errors. In the meantime, we need to consider those kind of business metric. It's because you want to and make more and more money. Sometimes making more and more money and versus your model to be more and more accuracies, like more and more accuracy. It doesn't line perfectly, so that means you need to balance both of this. Wow. And also you need to pick, and in general, what you do is you pick a model family, then you select proper hyperparameters. For example, if we're choosing the trace model, we're going to talk about that. The maximum depth will be the right hyperparameters that we should be working with. The larger the maximum depth that we work with, the more complex problems or models that we are dealing with. And the same here with the neural networks, they will have like architecture, the depth, the width, the regularizations. And the more like depth or the width that we have, and the more complicated of the model that we have, right? So it, I mean, depends of how complicated models that you are using here. It also should match with the data complexities. So a little bit summarizations, because we only care about the generalization error. We care about this and the model complexity. So the model complexity is the ability to fit in like various different functions. It also should match with the data complexities. The data complexity is the richness of the informations, right? So like how complicated of a data you work with. And the model selection, and during this model selection, we should match and choose the model or select the model that can actually match the model complexity and the data complexities. If it doesn't match, it will be either overfitting or underfittings. Okay, so at last we are going to talk about the model so validation. So so as I said, the most important thing is we want to minimize this generalization error. But in general, we don't know what is, that generalization error. So what we do is we approximate this generalization error by something called holdout test data set. That means we are going to have so you have a whole data set. You're going to take one part of data set, and usually about 20% of data set, and leave it out. You are not going to use that during the training process. So this is something called and to ensure this is and never being seen by and by this training of the models, you can only use that once and during the testing and the situations. But sometimes we are doing some validation as well. So and you can do like you can take like an additional 20% or 10% of your data that you can and that can be used like multiple times for this hyperparameter tunings. So this is different. So that's why in general, once we do the splitting, if you want to do hyperparameter tuning, you are going to maybe split your data into an 80% of training, 10% of validation, and 10% of your testing. So you are not going to use any testing data set during the training process. This validation data set will be used during training actually to find out the best parameters if possible. That's something called the validation data set. But usually there will be some like cases people like mention this is being like testing error, but usually sometimes people were referring to the validation error on the error on the validation data set. And then that's like totally possible as well. So there are a bunch of ways that and we can do. As I mentioned here, you can split your data into train and a validation data set. The important part is you train your model on your training set and use the error on the validation set to approximate this generalization errors. So that you ensure this validation set is never being seen during this training and the process, and then you choose the right parameter and the right hyperparameters to lower this generalization errors. And that's the most important things, because as I said, the only thing that matters is that generalization errors. That generalization error, and you need to choose the right hyperparameters to lower this generalization error. So usually this validation set, I would say, is about 20% of the validation. So I mean, this is, 10 or 20%. It depends on and what kind of problems. This is different from testing data set, right? So testing data set is something that is never being used during the validation. It's never being used for the training. It's just some data set just used for once as some like to tell the accuracy of your data. There are other ways to do the cross validations, which is called k-fold cross validations. So right here, we do this holdout validation. Just basically we split our training and the whole data set into training, validations, and the testings. And sometimes it just and training and the validations. So we just move one chunk of the validation data set out. That usually happens for the data is really large, like tens of thousands, right? So if we only have very limited data, so what we usually can do is called k-fold cross validations. So this is useful if we don't have, not sufficient data set. So what we do is we partition this training and the data into k parts. For example, right here, I'm going to partition into 3 parts. Then I'm going to create 3-fold, fold 1, fold 2, fold 3. In fold 1, these 2 will be my training. This will be my validations. On my fold 2, these 2 will be training. The middle one will be my validations. On my fold 3, the first 2 will be training. The last one will be the validation data set. So that means I'm going to set, as I said, the ith part will be validation, the rest will be training. Then you report this validation error average over the k-round. So that means you are going to report this validation error on the fold 1. You are going to report the validation error for the fold 2. You are going to report the validation error for the fold 3. Then average for this validation errors. So this will be your validation error you are going to report. And that's the approximate generalized errors that you're trying to minimize by doing this hyperparameter tunings. So basically, if you change your hyperparameters, and all these error will be slightly changed, that you're going to choose the optimal parameter such that all these validation errors, average the validation errors is minimized. But you have to be careful once you do this kind of splitting. So whether you're doing the holdout or K-fold the cross validate, because sometimes you are trying to split those kind of like non-RID data. For example, our like house sale data here. If we do this kind of non-RID data, this random data splitting may lead to underestimate of generalization error because these data are sequential data. You cannot using the future to predict the past because this validation set should not overlap with the training set in time. So this is very important. This happens a lot during the house sales and the stock prices because we cannot using the future to predict the past. That would be cheating. And also there will be some like example are highly correlated that's something it's also an issue as well. So these will not be non-IID data. For example, we are having the photos of same persons or the clips for the same videos. They'll also have a problem if we have highly imbalanced label classes. So that means they are not actually IID because and most of the time you're going to sample the data from one specific label class. And out of all these things, the first one, which is and the sequential data, is the most serious one because I saw a lot of people who don't realize the issue is trying to do this kind of like random splitting on the sequential data. For example, this house sale data that we have, if we split by 50% test on both random and the sequential splitting that we have, and we find out even with the linear regression right here, if we do random splitting, the training and the validation will be super, super small. However, if we choose the sequential and the splitting, that means I'm only going to split the first amount of data, then I'm using the current and the past to predict the futures. That will be this and a sequential splitting. And you will find out the validation error is significantly really, really large right here. So that just indicate, it's very, very important to use, the sequential ones. And otherwise, and we find out even with the linear regressions, with the random and the splitting, it can do very good job on the training and the validations. So you can see this actually shows a very big impact to this data set. Same here for this and the decision trees. If we're using sequentials, you will find out the best D will be 6, and the random that the best D is 13. It's like completely different. And it's like completely different errors. So basically we just simply couldn't do that kind of like random splitting for that kind of sequential data. In the later of the courses, in fact, in all many of homeworks that you're going to work with, you are going to work with the sequential data. I saw so many people trying to do this kind of like random splitting. As a result, and a lot of people saw a very good result, but turns out they are doing is completely wrong. And you see these kind of like very good result, but as a result, if you switch to sequential, everything just falls out, and everything becomes really, really bad. Just because of the random splitting, and you just like split the data and randomly. In fact, in the validation or like generalization error, they have seen certain level of data from the training data. So That basically says you are trying to using the future data and to predict the past. Of course, this will be always very good. General. So as I said, common mistakes, if your model performance is too good to be true, very likely there's a bug. So as I said, it's contaminated and validation and data set is number one reason. So basically, those validation set is not, it's not completely never seen before. During trainings, this contaminated and validation set sometimes is very hard to detect. You have to think through very, very carefully. But usually you would think about, things are so good, usually it's a bug. Sometimes it's also this validation data set could have like duplicate examples from trainings. This happens if we want to integrate multiple data sets. So you have to be careful to ensure those validation data set is never being synced during the training process. And that's why they can approximate the generalization error. As I said, information leaking from training ID and training to validations happens like non-IID, for example, sequential data, and also use future to predict the past. And this is also something that and it's similar to the sequential data as well. Okay, so this is very important. All these kind of like things point out one thing. If you see something that is like too good to be true, that's very likely to have a bug here. And that bug it may not be super easy to and observed. All right, and let's summarize what we have. And overall, if you have a data, and you're going to split into training, validation, and testing. Testing data is you only use once to evaluate your models, right? You just complete separate way. You're not going to touch that. For the validation data set, you can use that multiple times. And you can use like holdout validation set from training data set to actually tune and hyperparameters to ensure the generalization errors is minimized and during this process. So, and you can use this validation set multiple times for model selections and hyperparameter tunings. So ideally, this validation data should be close to the testing data set. But the difference is your testing data set can only be used once. Your validation and the data set can be used multiple times. As I said, so improper use of validation and data set is a common mistakes that and lead to like overestimate of the model performances. For example, they might have contaminated like validation data set. That's top one reasons of the common mistakes during the practical machine learning trainings. All right, so this is the concepts. In the next video, we're going to talk about how we actually program it out and using code to actually demonstrate this whole idea. All right, so that's all for now.